This is Brad, and welcome to the Analog Universe. This is episode 1, Einstein's Error. On this channel, we're going to talk about a lot of things like the theory of relativity and quantum mechanics, but don't worry if you don't understand a lot about physics and things like that, because we're not going to get too far into the weeds, and I'm going to explain everything you need to know as we go along. So, on this channel, we ask questions like, what if? What if you lived in 1491? Would you have believed that the world is flat? Some people did. Would you have believed that the Earth is the center of the universe? Everybody did. That's what they were told by the physicists of their day, or natural philosophers as they called them. They were told that God ordained the Earth as the center of the universe, and the sun, the moon, and the stars all orbited around the Earth. So everybody believed that. So what does that have to do with our episode today? Well, in our episode today, that's the first question. What if the universe we've been told exists, that everybody has been told exists? What if that's not the real universe? Just as the universe that people believed in 1491 wasn't the correct explanation of the universe that they really lived in. And so specifically my question is, what if Einstein hadn't made his mistake? And for you physics nerds out there, no, I'm not talking about the cosmological constant. And for everybody else, don't worry about it. That doesn't really matter for us today. But a little background first. Here's Einstein's theory of relativity as far as we need to know it for our purposes today. Einstein came up with his first theory of relativity in 1905. Yes, there were two theories of relativity, but we'll get into the second one later. But his first theory of relativity, known as his special theory of relativity, works like this. There's an absolute cosmological speed limit. Nothing, no matter what, can go faster than the speed of light. Say you're in a spaceship, and this is a super fast spaceship, and you're going 99% of the speed of light. Okay, and so you double power to your thrusters. Well, you might go 99.99% of the speed of light, but you're not going to reach the speed of light. So you double power to your thrusters again. And now you might be going 99.999% of the speed of light, but you just won't reach the speed of light. It can't be done. Now here's another part of the speed of light. And this one's a little weird, but stay with me. It's his theory. Say you're here on Earth, and you're watching a spaceship travel off into the cosmos, and it's going 99% of the speed of light. Okay, now you're here on Earth, and you see light travel away from you at 186,000 miles per second. That's how fast light travels in a vacuum. Okay, but say I'm on that spaceship, and I'm traveling at 99% of the speed of light. I'm also seeing light travel off in front of me at 186,000 miles per second. So you say, okay, I'm standing here on Earth, and I'm seeing light go away from me at 186,000 miles an hour. You're traveling 99% of that speed, yet you're still seeing light travel away from you at the same speed, 186,000 miles a second. Something's got to give here. And yeah, Einstein says, yes, in fact, something does give. And what gives is time. The observer here on Earth, when you're watching my spaceship, you're seeing time move for me in the spaceship at a slower rate than it's moving on Earth. That's the relative part of the theory of relativity. Time is relative. Okay, now we get to Einstein's error. Did he make a mistake? You tell me. Einstein, of course, didn't have super fast spaceships, and he couldn't test his theory the way we're talking about it here today. What he did have, and all he had, was equations that explained how light worked. And he came up with his theory of special relativity based on what he saw in these equations. Okay, so he's looking at these equations, and what he notices is time slows down for someone who's getting closer and closer to the speed of light relative to a stationary observer. So this and some other things led him to believe that time slowed down for someone who approaches the speed of light. And by the way, he said we don't live in the universe that everybody assumed we lived in up to that point. The universe everybody assumed we lived in was a universe where there was some universal medium through which light propagated. They called it ether at the time. And that light traveled in waves through this medium. Einstein, for reasons we don't need to get into right now, said that we don't live in that universe. There's no universal medium through which light travels, but light travels on its own through individual packets of energy, energy packets we now call photons. But let's say we were back in that universe that existed before Einstein, that there is some universal medium and that light travels in waves through that medium. Just as waves are propagated by the water that they're in, or sound waves are propagated through the molecules in the air in this universe, a universe I'm calling the analog universe for reasons we'll get into in a future episode. Light waves would be propagated through this medium, just as sound waves are propagated through the molecules in the air. Okay, so what would happen if we lived in that universe? In that case, here's what would happen. Say you're here on Earth, and I'm in a spaceship traveling away from you. I'm in that spaceship, and I've got a big blue beacon on the back of my spaceship. And you're watching me here on Earth. And as I'm traveling 100, 200, 300 miles an hour away from you, you're not seeing much change because 300 miles an hour is insignificant compared to the speed of light, which is 186,000 miles per second. Okay, but as I continue to accelerate away from you, and I'm going 60, 70, 80, 90% of the speed of light, what you start to notice is that the blue light that you're seeing from the beacon on the back of my spaceship is starting to change. And it starts to change through all the colors of the spectrum, from blue all the way down as I get closer and closer to the speed of light to red. Because in our visual spectrum, blue has the wavelengths that are closest together, and the wavelengths of red light are the furthest apart. So in effect, what's happening is you here on Earth are seeing fewer and fewer wavelengths reaching your eye as I get closer and closer to the speed of light. Here's what's happening. I'm in my ship and my beacon sends off a wave of light. But before it sends off the next wave of light, it has traveled forward some distance. And then it sends out a second wave. And it travels forward and sends out another wave. So those wavelengths are farther apart the faster I go and the closer I get to the speed of light. So it appears to you on Earth that time is slowing down for me because you're seeing fewer and fewer wavelengths per second. So the same effect as in Einstein's universe. For the person stationary on Earth, it appears that travelers traveling near the speed of light In a universe where light travels in photons, not waves, and time is relative, what the observer on Earth sees is time slowing down for the traveler going at the speed of light. In Einstein's universe, time is actually slowing down for that traveler. But in our analog universe, the person stationary on Earth watching somebody get closer and closer to the speed of light sees the same thing that a person would in Einstein's universe. And again, it appears to the person on Earth that time is slowing down for the traveler because the person is seeing fewer and fewer light waves per second reaching us from that traveler. But in our analog universe, time is not actually slowing down for that traveler. It's just an artifact of the fact that we're receiving fewer and fewer light waves per second from that traveler. And that's just as the equations that Einstein was looking at predicted. The closer and closer the traveler gets to the speed of light, for a stationary observer observing that person, the longer and longer the wavelengths are going to be that are observed coming from that person going near the speed of light. So what would that mean for us in our analog universe? If I had a giant clock on my spaceship and you were looking at that here on Earth, you would see my clock slow down. It would appear to you that time is going slower for me. And by the way, in our analog universe, there's no cosmic speed limit. There's no theoretical reason you couldn't exceed the speed of light. Now, there are lots of other problems with that, and we'll get into some of that in later episodes. But there's not the cosmological speed limit that there is with Einstein's special theory of relativity. It's just that in our analog universe, if it were possible to accelerate somebody past the speed of light, you wouldn't see the light from their spaceship anymore because they're going faster than those waves actually can travel in the universe. Okay, so that's a second possibility, one that Einstein didn't consider, and it's all consistent with the equations that Einstein was looking at. Is it right? Was Einstein right? I'm not arguing that I'm right and Einstein was wrong. What I'm saying is here's a second possibility that for the last 100 years, nobody's considered. And Einstein's error was not that he got his theory wrong necessarily, but that he failed to consider both possibilities as an explanation for the phenomenon that he was seeing in objects nearing the speed of light. And if he did, then we could look at both possibilities and say, okay, which one's right and which one's wrong. The second possibility, the analog universe, is kind of nice because you don't get odd results like the speed of light always remaining the same for every observer and time slowing down for some observers compared to others. But we don't know whether it's right or not because no one's ever considered it. Once Einstein's special theory of relativity gained acceptance, people stopped asking the question. I'm just saying, is it time to start asking these questions? And here's why I'm saying that. It's been over 100 years since Einstein developed his special theory of relativity. And quantum mechanics has been around for almost 100 years. And in that time, there's been massive, massive efforts to square these two theories, to make them mesh. Einstein himself was a young man when he developed his theories of relativity, and he spent the rest of his life trying to reconcile the two theories. But he couldn't do it. But way beyond Einstein, thousands of physicists have worked on these problems. And these physicists, if they're not the smartest people in the world, they're among the smartest. They're just scary smart. And they've worked and worked on this for 100 years and they can't get these two theories to mesh. And there's other problems with these theories that we'll get into in later episodes, but what I'm saying is there's just been massive, massive amounts of the greatest brain power on Earth trying to reconcile these theories for 100 years. And they can't be reconciled. But we've always looked in the same direction. We've always assumed that relativity is correct, that there's no flaws in the theory of relativity, and same with quantum mechanics. So all of the effort that's been made has been made making the assumption that these theories are correct, that there's no other explanation like the analog universe that might help explain some of this stuff. And so I'm saying, is it finally time to look in different directions, to consider an analog universe? Or perhaps you have an idea. But my goal here isn't to say I'm right and Einstein was wrong, or to get my views across on this. My goal is to start a discussion. So it dawns on me that there might be a way to test this hypothesis. I don't have the math skills to do this, but for somebody who has the math and knows the equations of relativity, plot a graph. On the x-axis is speed, and on the y-axis is time. And plot the graph showing as the distant traveler gets nearer and nearer to the speed of light, how time slows down. And you'll see the graph rising the nearer and nearer the traveler gets to the speed of light. Now, plot another graph, and this time we're going to assume an analog universe, just as I've been talking about here, where this distant traveler is letting off light waves in some kind of cosmic medium that are being propagated to us. And this time, figure out same x and y axes, and as the traveler is nearing the speed of light, they're going 90% of the speed of light, they let off a light wave. Okay, how much farther forward is that traveler going to travel before it sets off the next light wave? Okay, now traveling 95% of the speed of light, the ship lets off a light wave. How much farther forward is that ship going to travel before it sets off the next light wave? Okay, 99% of the speed of light. How much farther forward is the ship going to travel at that point between each successive light wave? And you'll come up with a graph showing a greater distance between each light wave, or you could translate that into the appearance of time slowing down for that particular traveler. Okay. Are those two curves that you've just plotted the same? Are they different? If they're different, looks like I'm wrong. It's science, right? You come up with a hypothesis, you test it. Sometimes you're right, sometimes you're wrong. If you're wrong, you move on to the next thing. I've had a blast putting this together. Thanks for your help, and we'll move on. But what if those two curves are the same? Will people who've spent their entire careers trying to work with and believe in Einstein's theory of relativity and trying to square that with quantum mechanics, are they going to accept now that they may have been barking up the wrong tree this whole time? I don't know. What I want to do, and my whole purpose here, is to spark that debate, to start a conversation. So if you do have those skills and you can plot those graphs, plot them and post your results below. I will be happy, no matter what the results are, to interview you here on this channel and we can talk about them and start a debate, or perhaps end it if that's as far as it's going to go. So join me here next time when we talk about the Ptolemaic fallacy. See you then.